excited to introduce our next guest up on the stage. We have Jeff from Ampere, who is the Chief Product Officer, and he's going to be talking to us about sustainability at the core with cloud-native processors. Jeff?
All right, thank you. So wow, a lot has happened over the last year. Thanks again. At Ampere, we remain committed to building the future of compute, to build the world's first cloud-native processors, which are the key to sustainability in the cloud. And that future is a reality here in Europe today. We have Hetzner offering dedicated servers that are based on Ampere. Scaleway and Glesis both have offerings based on Ampere, and there's going to be a lot of announcements over the next couple of months, as well as a lot here over the next couple of days at CloudFest. But as vital and as beneficial as the cloud is and has been over the past decade or more, I'm going to talk a little bit about the problems that the cloud is facing today. Today, the cloud is just not sustainable, and it cannot scale to meet our future compute needs. From global warming to natural disasters to out-of-control power costs, that we are in the midst of a crisis. And time is running out to solve some of the key technological problems. Now, the good news is that with 2 to 3% of the carbon emissions globally being contributed to by data centers, everyone here in this room can help to solve this problem. And it's not just the demands today, the carbon emissions, the power consumption of data centers. It's also about the unabated demand for more compute over the next decade and what that in turn will do in terms of rising power consumption and carbon emissions. A couple of examples. So there's a housing shortage in West London right now. And there's a need for more and more housing in order to help control rising rent costs, scarcity of housing. The problem, though, is that in those same West London neighborhoods, data centers have moved in, they're consuming all of the power on the grid, and there's no additional housing builds possible until 2035. Another example, in Northern Virginia, instead of just using diesel generators for backup power, cloud providers are actually needing to use diesel generators for a large chunk of the day because the grid can no longer supply the amount of power required. Until new substations and transmission lines are built by 2027, those operators will have to keep running diesel generators or face a loss of power. And the list goes on and on. From power shortages to water usage in drought-affected regions, it's key that we invest in new technologies in order to reverse this trend. One thing is clear. At the heart of this is the fact that the cloud is inherently power limited, and unless we take steps to change the foundation of the cloud, we will not be able to continue the growth of the cloud. The cloud will become limited because of power. So even if you don't care about a more sustainable or a more economical cloud, which I think most people in the room here do, even just obtaining more power is becoming more costly, it takes a long time, and in some cases, it might not even be possible. Now, since servers are directly responsible for most of the power consumption and indirectly responsible for a big chunk of the rest, let's start there. So let's take a step back to 1998. That was the year that Intel created a version of the client Pentium 2 CPU called Xeon. Okay, maybe I went a little bit too far back. So as everyone knows here, the client-server model was popularized in the 1980s. And by around 1998, the data center market was dominated by Unix machines from Sun and HP, IBM, and DEC. And Linux was quickly gaining adoption. It was running on about 25% of the servers that year. Now, at the same time, Intel took these client products, adapted them for usage in data centers, and combined with these lower-cost server chips from Intel, as well as Linux, these started to displace higher performance Unix plus RISC-based machines in the data center. That brought down the cost. You went from $100,000 plus servers to cheap commodity hardware that could scale out very easily. Now, this enabled massive scale, and that's why we saw such a big growth in internet services and the precursor to the cloud in the 2000s. But that's no longer sufficient. And we've seen this many times before. What generally happens is that the usage model begins to change, right? We've seen this already over the last decade plus. We've clearly moved into a cloud infrastructure model. Software then changes in response. That then fuels further growth of the usage model. In the case of software here, we saw things like containerization and microservices get added to the mix alongside virtualization. And that allowed services to scale out more rapidly, and it allowed developers to iterate more quickly as well. However, it was the exact same client-based CPU that was being used. Again, not surprising. This is what happened in previous technology transitions as well. A new model emerges, software changes, and then about a decade in, the hardware starts to change to fuel further growth. And that's what we're seeing today. That new hardware has emerged. It's the cloud-native processor. But before I jump into the details of the processor and specifically what Ampere is doing in this space, I want to talk about what is needed. What is needed is maximum compute density within a given resource envelope. That includes power, cost, water, and space. As I mentioned before, ultimately, the entire cloud is limited by power. We have a limited amount of power in the world. A specific subset of that could be used for the cloud. Hopefully, that actually decreases, not increases over time. And so what that means is you have a fixed power limit per cloud that then turns into fixed limits at the data center level, fixed limits at the rack level, and ultimately the goal is to deliver the most compute in that envelope. So there's two main ways that general purpose compute can get delivered. One is to deliver more performance per core. The other is to deliver more cores. Basically, this is scale up versus scale out. Now, traditionally, the approach was to scale up by increasing the performance per core. And as long as Dennard scaling worked, this was an appropriate approach. You had single cores that were able to increase their performance by continuing to add more and more transistors without increasing the power consumption. The performance doubled roughly every 18 months, and the cost reduced. However, as Dennard scaling ended, you started to see multi-core CPUs from x86, somewhere around 2005. Now, optimizing client code for parallelism can be difficult, and there's also difficulties in licensing models with more legacy applications like EDA tools or VMware, and so you didn't see a lot of core scaling. The approach was to continue to scale up. Now, the problem, though, is that while that served us well for a period of time, it's the least efficient and least scalable way to scale out compute going forward. And anyone that's deploying cloud-native services knows this today. They know that the goal is to optimize for performance per watt versus performance per core, and to scale out massively across hundreds, thousands, maybe even millions of nodes. Now, since these trends aren't going to reverse with CMOS transistors, performance per core, scale-up scaling, that has been rendered useless. It's not efficient, and over time, it actually means that the total performance and total capacity available to the cloud would actually go down, again, because you're power limited. Now, the other approach is to scale out. Now, this is what cloud-native applications do. Cloud-native applications are scaling out across many, many nodes because monolithic applications already outgrew the infrastructure of the past. This allows for elasticity, resiliency, efficiency. So this is a perfect opportunity for us to change the paradigm from a hardware perspective. And so that's what we've done with the cloud-native processor. So because we care about performance at scale, at maximum efficiency, we developed a CPU specifically for the cloud. So what did we really do? So we designed an extremely efficient and well-balanced core from scratch. All of the IPC gains are power and area efficient. We designed the processor to perform at the highest levels across many, many general purpose workloads in the cloud. This is everything from web services, databases, caching, media encoding, AI inferencing, you name it. If it runs in the cloud, Ampere's processors run those workloads the best. These aren't accelerators. These are general purpose processors that are using transistors efficiently all of the time. And then we amortize these really efficient cores, that power, across many, many cores. These are real cores, not virtual ones, from hyperthreading. And then we maximize the utilization of every single core. And then we develop power management techniques that focus on reducing power during active usage. Your servers today, you expect them to be running at high utilization. You want power savings when they're active, less so when they're idle. And it's clear you can only change this paradigm, moving from an area of low efficiency, high performance to an area of high performance, high efficiency, by building something from the ground up, throwing out the old legacy technologies of the past and starting over again. And that's what we've done. Specifically, we delivered 128 cores back in 2021, years before anybody else. Those cores can be utilized by many, many users, all running their own applications without suffering from performance or security vulnerabilities. So we changed the game, and it's clear that the competition is nowhere close. The other thing is that the cloud is all about scale, right? It's not about a single application. It's about a whole entire workload. And so while you might be thinking, man, maybe my application doesn't scale really, really well across all of these cores, that's fine. We're not talking about a single application running on 128 cores. We're talking about your entire workload scaling across hundreds of cores. You know, and even talking with people who would fall into that legacy application camp, so some of the biggest in-memory databases in the world, you know, even they see that future scale-up is not an efficient approach. Even they are starting to adopt more of a cloud-native approach, seeing that the only way to move forward is to efficiently scale, otherwise their database performance will be inherently limited by the power availability. So if you're an application developer, if you're deploying service in the cloud, continue to plan for being able to use more cores. We have 128 of them. We have more to come, so don't be afraid to use all of those cores. If you can use them all, make sure that your applications, you make sure you're getting 2x the application scaling with 2x the cores. If you take a more scale-up approach, you're not going to see anywhere near 2x performance gains. And when looking at how you deploy your applications, look at the desired latency, hit that latency, and then scale out across many, many cores. If you had 1 million web requests per second, you would dial in the latency, hit your SLAs, and then scale across a massive number of cores. And that's why when we're talking about the performance, the metrics that really matter, we are really looking at things like performance per rack. And if the goal is aggregate performance across real-life workloads, then the ideal metric is performance per rack under a specified rack power. This takes everything into account. This normalizes for power, for space, for cost, and everything's about scale. And you can see here, with this type of an approach, Ampere, we're delivering 2.5 times greater performance per rack versus Intel. Okay, this is not 53%, 2.5 times more performance than Intel, 1.7 times more performance than AMD. So clearly a massive shift in the scale that your cloud applications can achieve. So a little bit more, why does performance per rack matter? If I'm a data center operator, I have a single data center, I have a fixed amount of power. Ultimately, that fixed amount of power and the fixed amount of space I have means that each rack has a specific power limit, and I want to deploy the most compute per rack. So Ampere processors excel at that. This will result in the most capacity, the most compute in your data center. Now, maybe you're just a cloud user and you don't have any idea what's going on in the data center. That's fine. You're still going to see the benefits, the efficiency benefits, the cost benefits. Those are going to be passed forward in terms of reduced dollar per performance or increased performance per dollar for your applications. And increasingly, you're probably starting to ask questions about how much carbon is being emitted, how much power is being consumed by my cloud provider. So ask those questions. And make sure you ask the questions about specifically how much carbon is being emitted, how much power is being consumed by my specific application on the specific type of servers I'm running on and the number of servers that I'm running on. Ampere processors are going to consume a lot less power and emit a lot less carbon than those that are based on x86 CPUs. So if you can maximize the performance per rack, you've achieved the highest overall capacity in your data center. Now, why are we talking about things at the rack level? Now, it may, For marketing purposes, performance per core might provide some superficial benefits here and there, but again, everything in the cloud is about scale. It's not about running on single big machines like in the client space. It's about running massive workloads at scale. It's about a complete system running on more than one core. It's about the footprint and the cost of running your entire service. So, since performance per rack is what matters, clear choice is Ampere and our Ampere Ultra family of processors. You'll get high performance all the time, maximum capacity, no noisy neighbors. You can run at maximum utilization, the lowest power. The net result is 4 times more cores, 2.8 times less power, using a third the space, 2.5 times performance per rack. The other thing to keep in mind is you might not need to scale memory the same way that you've typically done in the past. You may want to scale your cores separately than memory capacity. This is why people like OCI have introduced flex shapes, where you can scale cores and memory separately. So look at your application, see if you can benefit from more cores, whether you actually need more memory as well. The other thing, when you're running Ampere processors, you can run at a lot higher utilization. We designed these processors to run at 80-90% utilization, run all those cores. You're going to have the same amount of headroom at 80-90% utilization on Ampere processors as you would at 40-50% utilization on x86 processors. So that's another 2x gain in performance on top of what I already mentioned before. The other thing is you don't need to change your current data center. These things are easy to cool. 128 cores, 125 watts. You can use your existing data center infrastructure, no change in thermals, in order to achieve the performance that you need. You know, I saw a real-life example of this a couple months ago here in Europe, visiting a data center. It was a 50-year-old data center, but a really complex customer, one of the most technologically savvy labs in Europe. Their problem is that they've had the same data center space and the same power footprint for 50 years, but they have to keep increasing their compute density. Walking around their data center, I saw a lot of half-full racks because they've already hit the rack-level power limits, and they just can't supply the data center with more x86 servers. And what this means is that over time, instead of their compute increasing, they're actually seeing decreasing compute capacity over time. So they benefit perfectly from our Ampere cloud-native processors. And to hear more about someone else who's benefiting from our processors, I do want to bring out Jan Gierik from Scaleway to talk a little bit about what they're doing with our Ampere cloud-native processors. Yeah, thanks, Jan Gierik.
Oh, it's very nice to be here and to be able to talk a bit about what we do with Ampere. And it's kind of exactly what you said, the power footprints, scalability that we have. And what we are able to do today is being able to have way more compute into the less footprint, because we are limited at a rack size at some point. You can increase the power, but we cannot cool it. So it just doesn't make sense to increase the density. And we have the same problem as what you just said, half full rack, a third of full rack, because we cannot fit and cram more compute in it. And with Ampere, what's very interesting for us is that we are able to increase the density on our rack and using all the power for switch. It's kind of a trivial thing, but switching nowadays, 25G, 100G, it's extremely expensive, and I want to be able to use all the port of the switch around that. What's very interesting is that we are running one of the most sustainable and power-efficient data centers currently in Europe, and using Ampere to do the same, and having it's nearly an order of magnitude difference between the power of an x86 core rather than an Ampere core. It's extreme, and it's perfect for us to be able to offer more for less on our customers. So
no, that's great
really
to hear.
Great.
Yeah, and you're the first French provider that
Yes.
is providing Ampere processors out to your customers.
Yeah, and it's available right now, and just test it and see how it feels to use Ampere. And it's the discussion we had with René not that long ago. Nobody's going to care anymore what's underneath. If it's cloud-based, it's just going to run your application. If your application is going to work, if it's x86 or ARM, nobody's going to care. It's just going to run, and it's running as good as even better on x86, depending on the application. It just makes sense.
Yeah, that's great to hear. Thanks, Jan Gierik. It's been great partnering with you on this. Yeah, I'm really excited to see what else is coming here soon.
Oh, so it's going to be great news very, very soon from us. Thank
Awesome.
you so much.
All right, thank you very much. So as you saw there, you can go and start running on Ampere servers today at Scaleway. Now, another thing you can get out there and do, another way to get started would be, let's say you've got a data center full of a bunch of inefficient x86 CPUs. You know, if we're talking about those data centers in Northern Virginia, these are literal gas guzzlers that are out there. So you could go and partner with an OEM like HPE, go and recycle those servers, and then replace them with sustainable Ampere servers, like the HP ProLiant RL300 that's based on the Ampere Ultra family of processors. I'd like to call this the Cash for Clunkers program. So it's an easy way to improve your data center and help the planet. So, takeaway here is, if you want the maximum rack level performance, the maximum compute capacity in your footprint for cloud native workloads that are delivered via the maximum performance per watt, highest core count, use Ampere processors. Don't be afraid to scale to more cores. They're really efficient. Focus on fleet level, not core level metrics. Don't just focus on single instances. Focus on your entire workload. If you want optimal latency, performance consistency, and you want that high utilization at max performance, Ampere's your choice. And we're really disrupting the market and building the future of computing. We didn't just build a faster horse, we're building something entirely new. So if legacy x86 is like the combustion engine, we're the EV. I expect to see continued Ampere innovation, breakaway performance. This is the future of compute. By adopting our cloud-native processors, you'll be able to grow and see many, many times more performance per data center over the next decade than with a legacy approach. And so a couple things. If you're ready to get started, go ahead, check out our Ampere-ready software. You can go check out over 100 applications, get started running right now. Let us know if you want us to add more applications. You can assess your current stack using our workload briefs and solutions guides. Go and evaluate using the right performance, the right energy metrics. As I've mentioned repeatedly, power matters. Start using packages and tools from your favorite repos like Bitnami now, GitHub, the cloud marketplaces. You can get started on a number of different cloud instances worldwide. Scaleway, obviously, Hetzner, and then other global providers. And then engage with the Ampere developer community. And lastly, just check out our booth, as well as there's a panel discussion at 12:35. We'll be talking about building sustainable data centers and go a little bit deeper into some of these with some of our great partners. And then also check out Ampere servers in some of our partner booths. They're at Alma Linux, Boston, Glesis, as well as Gigabyte. So thank you, everybody. Have a great CloudFest.
No, you don't get to leave yet. You don't get to leave yet. It's not that easy. All right, so hold on. Now, it's been 10 years since I've had my hands in the data center. But I can tell you, in fact, I probably still have a pulled muscle from racking servers and putting in the data arrays and just getting everything set up. So I'm looking at that. I can visualize a hosting data center in my head to this day. What would an Ampere data center implementation be different? What would I see differently?
Yeah, well, the good news is it doesn't look that different at a high level. It's the same standard racks that you are used to, 19-inch racks. You don't need to go and overhaul the cooling system. Whatever you've been doing with cooling today, you can go and use that. What is going to differ, though, is you're going to see denser racks. You're going to be able to pack in more CPUs, more servers per rack, because you've got the power to do it. So you're going to be able to more effectively utilize all of that space and more effectively utilize the power capacity that you have for your data center.
Okay, so one more question. I heard you say something towards the end there about Ampere-ready solutions or Ampere-ready applications. Give us some examples. What does that mean?
Yeah, so what we've done is, in order for people to get started, we've gone in and we've tested over 100 different applications. These are open source applications, things from Memcached, WordPress, TensorFlow. And so we've gone in, pre-tested those, and then we can direct you into the right repos if you want to go and grab the Ampere-enabled container off of GitHub. You got links there, so it's really easy for somebody to get started. Pre-tested, you know it works, and you're going to get great performance out of the box.
I'm going to follow up with that one question, because I heard TensorFlow, which everybody knows is kind of an AI thing right now, so that's cool. But what about databases? Yeah,
databases is a key area for us. So whether you're running something more like a caching, like Redis or Memcached, or whether big scale-out databases, MongoDB, MariaDB, Cassandra, those are all awesome applications to run on Ampere. You're going to see amazing performance.
It all works, no problem.
It all works, no problem. Anything that's open source out there likely works. A lot of the legacy box products work too, but open source stuff, that's your easy way to get started. All works.
All right. Thanks, Jeff. Appreciate it.
Absolutely.
All right.
Thank you.
Thank you for coming. Everybody.